Hi, my name is Kevin Chen, and I'm going to be presenting my results from Lab 1 charge tapes from my Physics 22 class from Georgia Tech. So in this presentation, I will start with an introduction that includes the findings, and then I'll move on to the key physics principles that are involved in this lab. Next, I'll provide the initial conditions for the experiment and go over the design and calculations of the observed model. I'll then present my computational model from GlowScript, as well as go over assumptions and experimental errors. Then lastly, I'm going to answer some discussion questions. The purpose of this lab was to observe the interaction between charged pieces of tape and approximate the excess charge on a piece of tape. A computational model was also created on GlowScript to simulate the results. It was discovered that when a charged tape was placed 15 millimeters above another charged tape that was initially bent in a U, that bottom tape rose to the top tape. The final charge of the tape was 5.53 times 10 to the negative 9th power, and dividing this by the charge of an electron produces 3.45 times 10 to the 10th power, which is the number of electrons transferred. Moving into some key principles in physics, the gravitational force equation, which is the force of gravity, is equal to the mass times gravity. It allows us to find the downward force on a piece of tape. Since the tape is floating, by Newton's second law, the change of momentum is zero. So it is an equilibrium and the net force is zero. The attractive electric force from the top tape on the bottom tape acts in the positive direction to balance the negative charge from the force of gravity. Since the electric force and force of gravity are the only forces acting on the tape, they are equal in magnitude and opposite in direction. So the force of gravity is equal to the electric force. And the electric force can be calculated using Coulomb's law. Going to the initial conditions, the length of the tape was 12.5 centimeters, which is 0.125 meters. The width of the tape is 1.9 centimeters, which is 0.019 meters. And the mass of the tape was estimated by multiplying 1 gram per meter by the tape length, which is 0.125 meters, and then dividing it by 1,000 to get the kilograms. And so we got 1.25 times 10 to the negative 4 kilograms. And then the distance between the two tapes before the bottom tape began rising to the top tape was 15 millimeters, which is 0.015 meters. In this experiment, we stuck two pieces of tape together before peeling them off. We laid one piece of tape between two books and it bent in a U shape. When we lowered the other piece of tape around 15 millimeters above it, the lower tape moved upwards. The force of gravity from the Earth and electric force from the top tape were the only forces acting on the bottom tape. Moving into the calculations from the observed model, we know that the magnitude of the force of gravity is equal to the mass times gravity, and the mass of the tape is 1.25 times 10 to the negative 4th, times the g constant, which is 9.81 meters per second squared, and this gives us 1.226 times 10 to the negative 3rd in newtons, and the force of gravity is equal to the electric force, based on the F-net equation. So the magnitude of the force of gravity is equal to the magnitude of the electric force, and so the electric force is also equal to 1.226 times 10 to the negative 3rd newtons. And to find the charge, we find the square root of the mass times the gravity times the distance, or r squared, divided that by the k constant, and this gives us 5.53 times 10 to the negative 9 coulombs. And taking the charge and dividing it by the charge of an electron, which is 1.602 times 10 to the negative 19th, it gives us 3.45 times 10 to the 10th, which is the number of electrons transferred. This is my computational model from GlowScript and my calculations to find the force of gravity, the electric force, and the E field. And as you can see in the simulation, the force of the gravity and the electric force oppose one another and produce a net force of 0. The E field arrow was scaled down considerably, and the magnitude of the charge of a single piece of tape was calculated to be 5.53 times 10 to the negative 9th coulomb. Moving on to the assumptions and experimental errors, we assume that the charges from electrons are evenly distributed and that the tape was treated as a point charge. We assume that each U-tape had about the same charge that was evenly distributed along the tape length, and some experimental errors were inaccuracies when measuring the distance between the tape, and we also ignored air resistance. So moving to the discussion and conclusion, to answer the what-if question, the same result would occur if the charges of protons and electrons were swapped. The only difference would be the labeling, which would be swapped between the negative and positive charges. And it's important, and to answer the why question, It is important to handle the charge tapes as little as possible because your hands are conductive and causes the charges to be transferred out of the tape. When the charge tapes come in contact with your hands or other objects, electrons move between the tape to the objects, which causes the tape to lose its net charge. So that brings us to the end of the video. Thank you for watching.